We are watching something extraordinary unfold in real time, and the more we learn, the stranger it becomes. The interstellar object designated 3I Atlas, a visitor from beyond our solar system, is now revealing features that have scientists split between cautious analysis and genuinely unsettling questions. As this comet-like body moves farther from the Sun, the quality of imaging has paradoxically improved, and what astronomers are seeing is deeply puzzling. The most striking feature is an anti-tail, a structure pointing in the opposite direction from the primary tail, defying the simple expectations of how these objects should behave. This is not just a curiosity. This is a phenomenon that challenges our understanding of orbital mechanics, dust dynamics, and perhaps something more fundamental about the nature of 3I Atlas itself. The debate has intensified dramatically in recent days, with one prominent astronomer going so far as to suggest that what we are observing is not a natural object at all, but a craft executing a programmed mission. Whether that claim holds any merit or represents speculative overreach is what we are here to examine, because the data coming in right now is both fascinating and deeply ambiguous. If you want to follow this story as it develops, and trust me, it is developing fast, make sure you are subscribed to this channel, because we will be tracking every observation, every analysis, and every conflicting interpretation as they emerge. Let's start with the anti-tail itself, because this is where the mystery begins. Anti-tails are not unheard of in cometary science. They appear when Earth passes through the orbital plane of a comet, creating a visual alignment that makes a thin trail of dust appear to point toward the Sun instead of away from it. It is an optical effect, well understood, documented in numerous comets over the years. The problem is that this explanation does not work for 3I Atlas. Earth has not yet crossed the plane of the object's orbit, and yet the anti-tail has been visible for an extended period, not just a day or two, as you might expect from a fleeting alignment. Researchers have now suggested that this feature may have been present since the object was first discovered, meaning it existed even before 3I Atlas passed behind the Sun and re-emerged on the other side. This is where the established model starts to crack. If the anti-tail is not an optical illusion caused by our position relative to the comet, then what is it? Is it a real, persistent structure being generated by the object itself? And if so, what mechanism could sustain such a feature over weeks or even months? These are not rhetorical questions. These are the exact problems that astronomers are grappling with right now, and there are no clear answers yet. The distance between 3I Atlas and Earth is shrinking. As of this past Sunday, the gap had closed to 300 million kilometers, and it continues to decrease. On December 19th, the object will make its closest approach to our planet, coming within 269 million kilometers before the two bodies begin to drift apart again. That is still an enormous distance, more than the span between Earth and Mars at their closest, but in astronomical terms, it is near enough to allow for detailed observation. Every telescope that can be trained on this object is being used, and the data is pouring in. What astronomers are particularly eager to see is whether the anti-tail changes when Earth does finally cross the orbital plane of 3I Atlas. If it behaves like a normal cometary anti-tail at that point, it would suggest that the current structure is somehow anomalous, possibly driven by forces we have not yet identified. If it does not change, or if it changes in an unexpected way, that would deepen the mystery further. Let's look closer at the data, because the details matter here. The anti-tail is not just visible, it is sharp and well-defined in recent images, which suggests a concentration of material that is not simply diffusing into space, as you would expect from loose dust. This could indicate active processes, either outgassing or something more complex, that are shaping the structure in real time. But the anti-tail is only part of the story. What has truly electrified the scientific community and divided it sharply is the trajectory of 3I Atlas itself. On March the 16th, 2026, the object is projected to make a close approach to Jupiter. Not a collision, not even a particularly close pass by the standards of planetary flybys, but a specific, targeted approach that lands the object at a distance of approximately 50 million kilometers from the gas giant. Here is the crucial detail. That distance corresponds almost exactly to the boundary of Jupiter's Hill sphere, the region of space where the planet's gravitational influence dominates over the Sun's. This is not a rough approximation. According to calculations put forward by Harvard astronomer Avi Loeb, the predicted approach matches the Hill sphere boundary to within 60,000 kilometers. In a solar system where orbital mechanics are governed by gravity, momentum, and chaotic perturbations accumulated over millions of years, such precision is almost unheard of. Loeb has pointed to this as evidence that 3I Atlas is not behaving like a natural object. He argues that the trajectory has been deliberately adjusted, fine-tuned through what he calls non-gravitational acceleration, a term that in conventional cometary science refers to the reactive thrust produced when volatile materials evaporate from a comet's surface and vent into space. But Loeb is not using the term conventionally. He is suggesting that the acceleration observed in 3I Atlas is not random, not the result of chaotic outgassing, but controlled and purposeful. So, what does this actually mean? If Loeb is correct, and that is a very large if, then 3I Atlas would be the first confirmed artificial object from another star system ever detected by humanity. The implications of that are staggering. It would mean that somewhere out there a civilization exists or existed with the capability to construct interstellar probes and send them across the void between stars. It would mean that we are not alone, and more than that, it would mean that other intelligences have visited our solar system not in myth or speculation, but in documented, observable fact. Loeb's hypothesis goes further. He suggests that the object is not simply passing through, but executing a mission. Specifically, he proposes that the close approach to Jupiter is designed to deploy a swarm of robotic probes into the planet's atmosphere, devices that could create what he describes as a flying base, composed of autonomous balloons or similar structures. The choice of Jupiter over Earth, according to Loeb, reflects the technological limitations of whoever built the probe. From light years away, detecting a planet like Jupiter would be relatively straightforward due to its size and gravitational influence on the parent star. Detecting Earth, a much smaller and less massive world, would require far more sensitive instrumentation. If the builders of 3I Atlas were operating from a distant vantage point, they may have only been able to identify the largest planets in our system, and thus targeted Jupiter as the most accessible destination for study. This contradicts what we previously thought about interstellar objects. When Oumuamua, the first confirmed interstellar visitor, was detected in 2017, it too exhibited anomalous acceleration that could not be fully explained by outgassing. Loeb proposed then that Oumuamua might be an artificial light sail, a hypothesis that was widely criticized and largely dismissed by the broader astronomical community. The discovery of 3I Atlas, initially catalogued as Comet Borisov when it was thought to be the second interstellar object, seemed to support the more conventional view. Borisov looked and behaved like a comet, with a clear coma and tail consistent with sublimating ices. But as observations of 3I Atlas have continued, the picture has grown murkier. The anti-tail, the trajectory toward Jupiter, the non-gravitational acceleration that appears to be precisely calibrated rather than chaotic, all of these elements are pushing the boundaries of what can be comfortably explained by natural processes alone. It is important to state clearly that Loeb's hypothesis is not accepted by the majority of the scientific community. Sergei Bogachev, head of the Solar Astronomy Laboratory at the Space Research Institute in Russia, has acknowledged that the approach to Jupiter is an interesting event, but he has called the conclusions about deliberate maneuvering pure fantasy. Bogachev and others argue that the apparent precision of the trajectory may be a coincidence or an artifact of incomplete data, or the result of poorly understood but entirely natural processes. The history of astronomy is filled with phenomena that seemed inexplicable at first, but were eventually explained through improved models and better observations. The rings of Saturn, the canals of Mars, the pulsations of quasars, all were once mysteries that sparked wild speculation before being resolved through patient scientific work. It is entirely possible, perhaps even likely, that 3I Atlas will follow the same path, that as more data comes in, a natural explanation will emerge that accounts for all the observed features without requiring the existence of alien engineers. But here is where the intrigue deepens. The upcoming observations in March 2026 will be critical. If 3I Atlas behaves as Loeb predicts, if it passes Jupiter at the expected distance and exhibits further signs of controlled maneuvering, then the artificial hypothesis will gain significant weight. If, on the other hand, the object's trajectory deviates from the predictions, or if the close approach turns out to be less precise than currently calculated, then the natural explanation will be strongly reinforced. Either way, we are about to get answers, or at least better questions. The instruments that will be observing this encounter include some of the most powerful telescopes on Earth and in space. The Hubble Space Telescope, the James Webb Space Telescope, and numerous ground-based observatories are all being lined up to capture as much data as possible during the flyby. Spectroscopic analysis will reveal the composition of any outgassing. High-resolution imaging will show whether the object's shape or surface features change, and precise astrometry will track any deviations from the predicted path. This is not a case where we are limited by technology or observational capability. We will get the data. The question is whether the data will be clear enough to resolve the debate, or whether it will simply add new layers of complexity. Now, I want to pause here and ask you something, because this is not just a story for scientists. This is a story about how we understand our place in the universe. Do you think 3I Atlas is a natural object exhibiting unusual but ultimately explicable behavior, or do you think there is a real possibility that we are looking at evidence of extraterrestrial technology? Drop your thoughts in the comments, because I am genuinely curious to see where the audience stands on this. The scientific community is divided, and I think it is worth hearing from people outside the academic bubble, people who are following this with fresh eyes and no professional stake in the outcome. And if you are finding this deep dive valuable, if you appreciate this level of detail and analysis, take a second to leave a comment with your perspective. It helps the algorithm understand that there is an audience for serious science content, and that means more coverage of stories like this. Let's return to the question of non-gravitational acceleration, because this is central to the entire debate. In a typical comet, as it approaches the Sun, the increasing heat causes ices on the surface to sublimate, turning directly from solid to gas without passing through a liquid phase. This outgassing creates jets of vapor and dust that act like tiny rocket engines, pushing the comet in directions that are not purely gravitational. The effect is measurable but small, and it tends to be somewhat chaotic, varying as the comet rotates and as different regions of the surface are exposed to sunlight. What Loeb is claiming is that the non-gravitational acceleration in 3I Atlas is not chaotic. It is consistent, directional, and precise enough to steer the object toward a very specific target, the Hill sphere boundary of Jupiter. If that is true, it would require a level of control that is difficult to reconcile with random outgassing. You would need a mechanism that could produce thrust in a sustained and predictable manner, something more akin to an engine than a comet. Critics of this view argue that we do not yet understand all the ways that comets can outgas. There may be internal structures, vents, or reservoirs of volatiles that could produce more regular thrust patterns than we typically observe. There may be compositional differences between interstellar comets and those native to our solar system that lead to different behaviors. The problem is that we have very limited data on interstellar objects. Oumuamua is gone, already too far from the Sun to observe in any detail. 3I Atlas is still here, still observable, but it is also moving away, and the window for detailed study is closing. By the time the Jupiter encounter happens in March 2026, we will have had roughly a year and a half of observations, which is a decent baseline, but not enough to rule out all natural explanations with absolute certainty. There is also the statistical argument to consider. Loeb and others have pointed out that the probability of 3I Atlas encountering Jupiter at all is extremely low. Interstellar space is vast, and the odds that a randomly moving object would happen to pass through the inner solar system and then encounter a major planet within a specific distance range are vanishingly small. According to probability theory, 3I Atlas should have had virtually no chance of crossing paths with the outer planets of the solar system. And yet, here we are, watching it approach Jupiter with what appears to be almost surgical precision. Does that prove artificial origin? No. Unlikely events happen all the time, by definition. If you flip a coin 1,000,000 times, the specific sequence of heads and tails you get will be unique and statistically improbable, but it still happens. The fact that 3I Atlas is on this trajectory does not by itself prove anything, but it does raise eyebrows. It does make you wonder whether we are missing something fundamental about the nature of this object. The anti-tail the trajectory, the non-gravitational acceleration. All of these elements are interconnected. If 3I Atlas is a natural comet, then there must be a natural explanation that accounts for all of them simultaneously. If it is an artificial probe, then the behaviors we are seeing would make sense as part of a designed mission profile. The challenge is that both explanations require us to stretch our assumptions. The natural explanation requires us to accept that we are seeing a confluence of rare or poorly understood phenomena all occurring in the same object at the same time. The artificial explanation requires us to accept that an extraterrestrial civilization exists, that it built an interstellar probe, and that we are observing it right now. Both are difficult to swallow, but one of them has to be closer to the truth. What makes this moment so compelling is that we are not dealing with ancient history or distant speculation. This is happening now. The object is out there, moving through space, and we can watch it. Every night, telescopes are gathering light that left 3I Atlas hours ago, carrying information about its surface, its composition, its motion. The data is accumulating, the models are being refined, and the debate is intensifying. There is a sense that we are on the edge of something significant, whether it is a breakthrough in our understanding of cometary physics or a confirmation that we are not alone in the universe. Either outcome would be profound. The idea of robotic probes being deployed into Jupiter's atmosphere is particularly fascinating because it is not purely science fiction. We have sent probes to Jupiter ourselves. The Galileo probe entered the planet's atmosphere in 1995 and transmitted data for nearly an hour before being crushed by the immense pressure. The Juno spacecraft has been orbiting Jupiter since 2016, studying its magnetic field, its auroras, its internal structure. We know that Jupiter is a laboratory for extreme physics, with radiation belts that would fry unshielded electronics in minutes, winds that exceed anything on Earth, and a magnetosphere so vast that if you could see it from Earth, it would appear larger than the full moon. If an alien civilization wanted to study a gas giant, Jupiter would be an excellent choice. It is the most massive planet in our system. It has the strongest magnetic field, and it has a complex system of moons that are worlds in their own right. Deploying probes there would make sense from a scientific perspective. The question is whether that is what we are actually seeing, or whether we are projecting our own exploratory ambitions onto an object that is simply a comet with unusual properties. Loeb's reference to conscious balloons is intriguing but vague. What would such devices look like? How would they operate in an environment as hostile as Jupiter's atmosphere? Balloons on Earth rely on buoyancy, floating because the gas inside them is less dense than the surrounding air. In Jupiter's atmosphere, you could theoretically do the same thing, using hydrogen or helium to create lift. But the planet's atmosphere is mostly hydrogen already, so you would need something even lighter, or you would need to heat the gas to lower its density. And you would need materials that could withstand the corrosive chemistry, the intense radiation, and the crushing pressures at depth. It is not impossible. Our own engineers have proposed similar concepts for exploring Venus and the outer planets, but building such devices and deploying them from an interstellar probe would require a level of technological sophistication that is difficult to imagine. It would require not just the ability to travel between stars, but the ability to operate autonomously in a completely alien environment to adapt to conditions that could not have been fully predicted from light years away. Is that plausible? Could a civilization achieve that? There is no reason to think it is impossible, but there is also no evidence that it is happening here. The choice of Jupiter over Earth, as Loeb suggests, is an interesting point. If you are an astronomer in another star system observing our Sun from dozens or hundreds of light years away, what can you detect? You can measure the Sun's spectrum, its mass, its luminosity. You can look for periodic dips in brightness that might indicate a planet passing in front of the star, a technique we use ourselves to find exoplanets. Jupiter, being large and massive, would be relatively easy to detect. Its gravitational pull on the Sun would create a measurable wobble, and its transits, if aligned correctly, would be detectable. Earth, being much smaller, would be harder to spot. You would need more sensitive instruments, longer observation times, and probably a bit of luck. So, if you are planning an interstellar mission and you can only identify one or two planets in the target system, you would naturally aim for the ones you can see. That logic makes sense. But it also assumes that the builders of 3i Atlas are not far beyond us technologically. If they are thousands or millions of years more advanced, they might have no trouble detecting Earth-sized planets or even smaller objects. The assumption that they could only see Jupiter is based on extrapolating our own capabilities, which may not be valid. There is also the question of timing. Why now? If 3i Atlas is an artificial probe, why is it arriving in our solar system in the early 21st century? Is that a coincidence, or is there a reason? Did the builders somehow know that humanity would be at a stage where we could detect and study the object? Or is the timing purely random? If the probe was launched millions of years ago, there would be no way for its creators to predict what they would find upon arrival. They might have expected a lifeless system or a thriving civilization or something in between. The fact that we are here watching, analyzing, debating might be a surprise to them if they still exist at all. Or perhaps the probe is designed to operate autonomously, to explore and report back regardless of what it finds. These are questions that we cannot answer with the data we have, but they are worth thinking about because they frame the broader context of the discovery. Let's consider the alternative. Let's assume, for the sake of argument, that 3i Atlas is entirely natural. What would that tell us? It would tell us that interstellar comets can exhibit behaviors that are far more complex and varied than we realized. It would suggest that the processes of outgassing, dust dynamics, and orbital evolution are richer and more nuanced than our current models predict. It would mean that the anti-tail is a real phenomenon, driven by some combination of particle interactions, electromagnetic forces, or unusual compositional properties that we have not fully characterized. It would mean that the trajectory toward Jupiter, while statistically unlikely, is a product of the chaotic gravitational environment of the solar system, shaped by perturbations from multiple planets over the object's journey. And it would mean that non-gravitational acceleration, even in interstellar objects, can sometimes produce patterns that appear ordered but are actually the result of complex non-linear processes that we do not yet understand. All of that would be scientifically valuable. It would expand our knowledge, challenge our assumptions, and give us new tools for studying other objects in the future. It would not be as dramatic as discovering alien technology, but it would still be significant. The reality is that science often advances through the careful elimination of possibilities. You propose a hypothesis, you test it against the data, and you refine or discard it based on what you find. Loeb's artificial hypothesis is bold, and it is testable. If the predictions he has made about the Jupiter encounter are borne out, the hypothesis gains credibility. If they are not, it loses credibility. That is how the process is supposed to work. The problem is that public discourse does not always follow the same rules. In the age of social media and instant communication, hypotheses can take on a life of their own, becoming narratives that people invest in emotionally rather than evaluating dispassionately. The danger is that if 3I Atlas turns out to be a comet, the artificial hypothesis will be remembered as a failure, a cautionary tale about speculation run amok. But if it turns out to be something else, the skeptics will be remembered as the ones who dismissed the evidence too quickly. Either way, the story will be shaped as much by how people tell it as by what the data actually shows. Right now, as 3I Atlas continues its journey toward Jupiter, the scientific community is preparing for what could be one of the most important observational campaigns in recent history. Telescopes are being scheduled, data pipelines are being set up, and researchers are coordinating across institutions and countries to make sure that nothing is missed. The flyby in March 2026 will last only a brief period in astronomical terms, perhaps a few days or weeks when the object is at its closest and most observable. During that window, every piece of data will count. Every spectrum, every image, every measurement of position and velocity will be scrutinized for clues. The goal is not to prove or disprove any single hypothesis, but to gather as much information as possible so that the community can make informed judgments based on evidence rather than speculation. There is also the question of what happens after the Jupiter encounter. If 3I Atlas continues on a hyperbolic orbit, as expected for an interstellar object, it will eventually leave the solar system entirely, heading back out into the void. Once it is gone, we will have no further opportunity to study it directly. The data we collect now will be all we ever have, at least until we develop the technology to send our own probes to intercept such objects, a capability that is likely decades away at best. That adds urgency to the current observations. This is not a phenomenon that will wait for us to build better instruments or refine our theories. It is happening on its own schedule, and we have to keep up. If you have made it this far, you are clearly invested in understanding this story at a deep level, and I want to thank you for that. Science journalism thrives when there is an audience willing to engage with complexity, to sit with uncertainty, and to follow a story through all its twists and turns. If you found this analysis valuable, if it gave you new insights or raised new questions, please consider liking this video. It might seem like a small thing, but it genuinely helps the algorithm recognize that there is demand for this kind of content, and that means more deep dives, more investigations, more serious science reporting. So, if you are with me on this, hit that like button, and let's make sure that stories like 3I Atlas get the attention they deserve. In the end, what we are witnessing is a collision between the known and the unknown. We have models, theories, and expectations built on centuries of astronomical observation. We know how comets behave, how orbits evolve, how dust scatters in space. But 3i Atlas is testing those models in ways we did not anticipate. It is showing us features that do not fit neatly into the established framework, and that is both exciting and unsettling. The anti-tail that persists when it should not. The trajectory that aligns with Jupiter's Hill sphere to an almost uncanny degree. The non-gravitational acceleration that appears too precise to be random. Each of these could have a natural explanation, or they could be pieces of a larger puzzle that points towards something we have never encountered before. The next few months will be critical. As Earth approaches and then crosses the orbital plane of 3i Atlas, we will see whether the anti-tail changes, disappears, or remains stubbornly in place. As the object draws closer to Jupiter, we will see whether its trajectory continues to match the predictions, or whether it deviates in ways that support or refute the artificial hypothesis. And as more data accumulates, we will see whether the scientific community begins to converge on a consensus, or whether the debate continues to fracture along lines of interpretation and methodology. What is certain is that 3i Atlas has already changed the conversation. It has forced astronomers to confront the possibility, however remote, that interstellar objects might not all be natural. It has highlighted the gaps in our understanding of cometary physics and orbital dynamics, and it has reminded us that the universe is still full of surprises, that even in an age of sophisticated instruments and powerful models, we can still be caught off guard by something we did not see coming. This is the crucial detail that I want to leave you with. We do not yet know what 3i Atlas is. We have hypotheses, we have data, we have arguments and counter-arguments, but we do not have certainty, and that is okay. That is how science works. You start with uncertainty, you gather evidence, you test ideas, and you move incrementally toward understanding. Sometimes the answer is straightforward. Sometimes it is not. Sometimes the mystery deepens before it resolves. But the process is always the same. Observe, question, analyze, and repeat. Right now, we are in the observation and questioning phase. The analysis is ongoing, and the answers are still forming. By this time next year, we will have a much clearer picture. We will know whether the Jupiter encounter happened as predicted, whether the anti-tail behaved as expected, whether the non-gravitational acceleration was consistent or erratic. We will have more data, better models, and hopefully fewer unanswered questions. But there is also a chance that we will have new questions, deeper mysteries, and even more reasons to wonder about the nature of this strange visitor from the stars. That is the reality of cutting-edge science. You do not always get the answers you expect, and sometimes the questions themselves change along the way. What we are watching with 3i Atlas is not just an object passing through the solar system. It is a test of our understanding, our methods, and our willingness to consider possibilities that challenge the comfortable boundaries of what we think we know. And that, more than anything, is why this story matters.